next parameter we'll learn as learning rate, but you must understand, if you learn these parameters for one neural network model, which is MLP, 90% of these are same for all others. That means in one go you are learning similar parameters for all other neural networks. Okay. So this is kind of interesting. The same things will be used for other ones. Anyway, so next one is learning rate. Batch size we already saw. By default it is constant. Okay. So let's look at what are the different options that are available before we go. You have constant, you have inverse scaling, you have adaptive. Okay. Constant means constant value you will specify, usually 0.01 or 0.001. I will show the variation, what the difference is in between them. Okay. So learning rate behavior is what you are setting here. Constant means a constant number. Inverse scaling means gradually it will decrease. Okay. For each step it takes, it will start to decrease using a inverse scaling exponent of power. Don't worry about all this terminology if it's sounding too complex. For you, just understand, in the denominator it is using power function, so that it will decrease the numerator in steps. Initially, for first step the numerator will be very big, in next step the numerator will be small, and next step it will be even more smaller, then further smaller, so that way. Okay. So that is inverse scaling. Next is adaptive. Adaptive means it knows when to increase and when to decrease. Okay, learning rate will increase and sometimes it will decrease for each epoch. So that is adaptive. So these are the three options. Adaptive is usually used for stochastic gradient descent. Okay. Anyway, now that we know, we want to understand what gradient descent phenomena looks like and what learning rate means. Okay, see, this is what it is. So this is a very complex cost function. Actually this is very simple cost function. Complex means it will have even more crusts and troughs. Okay, so this is what cost function looks like when you plug it into a Hessian matrix and you plot a Hessian matrix. Sometimes some surfaces will be high, some surfaces will be low. Okay, as we know, Hessian matrix takes second order partial derivatives. It calculates for that for particular functions, and each value in that matrix, if you start plotting, this is how the surface will look like. Okay, one sample. Now our job is to decrease the error. How do we decrease the error? In that Hessian matrix, we have to pick a surface which has the lowest point, lowest steepest point. What we call it as local minima. That is the aim of this optimization algorithm, to decrease the error rate, to decrease the loss function, and loss function in turn decreases the difference between original y and y pred. And how do they do it? They do it by manipulating the m values by multiplying that learning rate with m values. So that's how they are doing it. Now learning rate means, see, this is x. If you alter the x, okay, that alters the learning rate. What is the learning rate here? Learning rate is alpha. I will modify the alpha and see what happens. So basically this is adaptive. See, as it comes nearer, so initially it is at the steepest point, at the tallest point. From tallest point it has to go to the lowest point. Okay. So when it has to go to the lowest point, initially see it is small, and then it is increasing, and here it is decreasing again. Okay. Notice the path. Notice it is bouncing. If your alpha is too high, it is bouncing there only. It is unable to figure out where the lowest point is. It is bouncing inside in that curvature only. If you further increase, see, it will keep on bouncing. Sometimes it will even come out of that lowest point. Okay, so that's why alpha should not be too high. If alpha is too high, it will never go to the lowest point, and hence it will never reach the lower local minima. Hence your loss function will never be minimal. Hence your model will never be accurate. Okay, so that's why you should have a alpha value which is small enough. At the same time, either it has to be adaptive. See, now I'm decreasing. See, if you decrease too much, you make it very closer to 0. If you make it 0, it will always be 0. What will happen? Your weight, which is your, here you can see mathematically, your position P of n will remain as P of n only. This alpha, if it becomes 0, multiplied to the function will remain 0. So it will never go. If you increase by little bit, make it very small value, it will take lot of steps to reach that lowest point. Okay, that's why it is important that you balance it. You have to have a point. You can't have bigger point, you can't have smaller point. It has to be very optimal number. Okay, this is what alpha does. Okay, do you hope this is you have better understanding now. I will show you another one. Let's just say your function is x square plus x. Okay, for this function, let's just say we are starting at certain value called 6. At 6, x-axis, look at the x-axis. At 6 I am starting, and y value is something else, and this curvature you are seeing is a cost function. Okay, cost function. And this line, red line you are seeing, is the slope. This slope is what you have to adjust. Now I'm starting at 6. I have set up at 6. I have set the learning rate to 0. Let me set it to 0.001. Okay, imagine how many steps I have to take. 1 2 3 4 5 6 7 8 9 10 11 12 13. Keep on, you have to keep on going until you reach the lowest of cost function. Cost function is the average of all the loss functions. Now loss function is directly calculating the error rate. Now error rate is directly dependent on the slope. All these are interlinked. So you're measuring the loss cost function versus the slope. See how many steps. If you keep it too small, you need too many iterations to arrive at that lowest point. Okay, if you keep it too big, let's just say 5. I will set it up again. If you set it as 5, see what is happening, it's not even showing up. Okay, let me keep it as 2. Not even 2, 1. Notice it will never reach that point if you set it as high. Our job is to keep it to such a point that it reaches this minimum point here or here. Okay, whatever is the minimum point, it has to reach there. So now I will keep it as 0.01. This is what I kept, I think 0.1. Okay, let me set it up again. See, it reached in just 13 iterations, it reached the local point versus 126 that it took for 0.01. If I set it as 0.25, let's see now. In 4 iterations it reached. Okay, let's set it as 0.5. See, it's not reaching. It reached this point, minimum point, and it stopped in 4 iterations. Okay, so this way, now further it's not moving. That is not good. Okay, anyway, these are the, I have attached, someone have put a lot of efforts, these folks. So that is why I say our data science community is very how do I put it, very hardworking. And see, someone has put a lot of effort in coming up with this. Who is this person? This person, I don't know the name, but you can check out their websites. Very good. I have attached the reference as well. Good sites. So this will give you better understanding. Okay, now you know what is learning rate. Learning rate is the alpha value or the small value that you multiply to the gradients, so that you multiply to the slope and intercept to modify them. Okay, and that small modification we call it as gradients. Okay, so model weights have to be adjusted with respect to the gradient of loss function. So that's why you have to take step sizes, and that step sizes, how much step size you take, determine how fast you reach the lowest of the cost function. So if you have two small value, 1 e minus 4 means 4 zeros are there. How do you read this? 1 e minus 4 means 0.03 3 zeros followed by 1. So that's how you read it. Okay, so moderate value is this one, and higher value is greater than this one. So if you have smaller value, it will reach the convergence is the point at which you lowest point you reach, so it will reach very slowly. Okay, if you have very high value, it will speed up the convergence, reach the minimum faster. Moderate means it balances somewhere in between, and this is what we want. Moderate is what we want. So disadvantages you already saw. If you have too small value, it may overshoot the minimum. Okay, too high value, sorry, this should be undershoot. Maybe while typing I might have made mistake. This will undershoot the minimum, that means it may never reach the minimum point quicker. That's what it is. So this may overshoot. You saw how we reached, how the gradient descent went out of the path here, right? So if you set it high, it will keep on toggling between that point only. So that is what we are saying here. Risk of overshooting the minimum is high, unstable, higher learning rate. Okay, you shouldn't use it when working with, and this you should use it when you are working with simple models, so that you can reach the convergence faster. And here slow convergence would be there, and here balanced approach. So these are the advantages and disadvantages of this. Now how do you tune it? How do you find out which is the right learning rate? For that you can do grid search. Again we'll talk about grid search in depth when we learn when we do that feature engineering class that I will take separately for you. Okay, so in that we will learn various concepts that are to be learnt in feature engineering. So there we'll see something called hyperparameter tuning, and hyperparameter tuning is a process of finding out the optimal values of the hyperparameters. So there the process is very simple. We'll consider a certain range of values and we'll pick the best ones out of that. The model will pick it, we'll just provide the values. So there, that is the one way of finding out the best learning rate. Next way is learning rate schedulers. Okay, you can dynamically adjust this learning rate which your solver do automatically. For example, adagrad you saw, right? It adapts the learning rate. Okay, you can use some variations of adagrads to allow the model to do the dynamic adjusting. That way you don't have to worry about learning rates. Next is warm-up strategies. Warm-up strategy means if you have already learned certain weights from previously, you can start with small learning rate and gradually increase the learning rate to higher value. Okay, that is another strategy. So this way you can learn the learning rates. Clear? Understood? Maybe you can give a like or thumbs up, so just to indicate. Okay. Next is warm start. Warm start is, let's just say, think about it. There is a serious problem in training models. As MLOps engineers and data analysts, you should know this. Let's just say you got the data, you trained the model, you did the prediction, you deployed the model, but tomorrow the trend changed. Okay, for example, in your hairstyles, okay, over the period of time, if you see, hairstyles have changed. There is a very good video made by someone on how the hairstyles have changed over the period of time. You can maybe Google it later on. I'm just giving one example. May it be hairstyles, may it be clothing styles. Okay, so if you notice, how we used to dress in 1980s, 1970s, 1960s, we no longer dress ourselves like that, right? Styles have changed. Now if the use case is to determine what type of design fabrics are selling the most, you can't rely on the 1970s or 80s or 90s data, right? That would result in the drifts. Now what we are saying is, when you're using a neural network, If you have already trained the model to learn the previous pattern and the new patterns have come up, you can, instead of starting the training of model from the scratch on the new data, that is a waste of too much compute. What we are saying is, we are going to use the previous weights as they are and slightly tweak them. We are going to initialize the same previous weights that we have trained from the model, and but slightly tweak them instead of starting from the scratch. That process we call it as warm start. Okay, warm start is nothing but you're going to use some sort of initialization techniques, wherein which you're gonna not train the model but rather build up on the knowledge that you have already acquired. Okay, so that process is called warm starting neural networks. And what does it, how it works, we'll learn that again. But what does it do? It allows you, essentially this warm start is the process that is allowing us to do transfer learning. Basically we can use the pre-trained models. Okay, we can use the pre-trained parameters and allow the model to converge faster. Okay, so you are no longer using the initial random weights but rather using the previous learned rates. This saves lot of computation time, lot of computational resources. Okay, now see, this helps. How are we using this? Let's just say you're using some NLP based models which have learned some semantics in the data. You can use directly that pre-trained model, modify it and use it for semantic analysis, no, sentiment analysis, or named entity recognition. Okay, a lot of things can be done with pre-trained parameters. If you have already learned what the data looked like previously, you can use the same thing on top of new data and get better results. Okay, this warm start is very very important. Next is better generalization you can do on the new data. Now if tomorrow the new data again goes back to the old styled clothes, you know, you don't have to rerun the model on the new data again, right? Model has already learned that. So that is another advantage, better generalization. Next is very very important, especially in financial data and data sets. What happens is, you get the data in increments. That means whatever the transactions people do today, okay, you'll have to increment that learning into the data. Okay, this I had practical hands-on for with this type of problem. I'll explain you a little bit here. We were working on a use case where we were trying to identify the customer behavior from the transactions they do. What the major challenge was, bank was ready to give only 3 months of data. Okay. What is this, Sachin? Okay, fine. So bank was ready to give 3 months of data, but the new challenge was, after training on 3 months of data, the new data that comes in every day, that had to be incorporated. Now one way you can think of it is, every day you will start training on the 3 months data plus one day of data. But that is not feasible. No, your training cost will increase each day. That means each day you have to spend hundreds of thousands of dollars for training. That is simply not feasible. So that is where incremental updates were done to the model. So either you add new layers of data and make those new layers of data learn from the latest data, or you modify the existing weights by slightly little bit. So this is one of the biggest challenge, okay, on incremental data. Okay, so that is where warm start comes up. You set a warm start value. So here you can see, so you can just check it. Warm start is false by default. You can set it to true. The moment you set it to true, couple of things happen. Okay, there are a couple of initializations that take place, that we will talk For example, glow rot initialization, HE initialization, those things will happen. Okay, we'll learn that in deep learning, but just understand that with this initializations, if you call the fit method on the new data, your previous learnings are retained. Okay, if you don't set it to true, all your previous learnings are erased. Okay, if you set it to true, some initializations happen. We call it HE initialization or glow rot initialization. Okay, so such initializations happen, wherein which those previous weights are retained, they are not erased. Okay, so that is where warm start comes into picture. Next is momentum. Momentum we talked about above. Okay, what momentum does is, it's just a technique to accelerate the training process. We want to improve the convergence of the gradient descent algorithms. We want this thing to go to that part very very quickly, to go from the top to bottom very very quickly. That is where momentum comes in. It's a technique. Okay, what it does is very very simple. Okay, so if you have it just, while you are updating the weights, okay, now you are not only considering the current gradients, but you are also taking the previous gradients into account. So basically, when you want to update, see, delta j is the cost function, theta is the slope or the weight, so beta is the step. Okay, step that you are taking. So what you are doing is, we call it momentum coefficient, beta. So what you are doing is, you are not only considering the beta value of previous step, you are also considering current step. This is current step, beta vt minus 1. You are considering the previous step also, 1 minus beta into delta, whatever this is, and this theta t minus 1 is from the previous step. So again, don't worry about mathematics. Okay, but just remember, this momentum is taking into account previous gradients also. By doing that, what now it knows is, it knows how the step was taken in the previous step and how it should take the step in the alpha, how it should take in the current step. So this way it knows where to converge better. Okay, so that's how it is able to speed up the convergence. Okay, anyway, so if I find an interactive demo, I will show it, but for now just remember that much. It uses the beta factor, momentum coefficient, and it also uses the gradient of the loss function j. Wherever you see j, either it is cost function or the loss function. Okay, so it uses the gradient of the loss function of the weights from the previous step. So in that, it avoids the local minima and it reaches the global minima. Okay, so that is uses of this. Disadvantage is, this beta function is very sensitive. Tweaking it is poor. If you choose it poorly, you will get poor results. And the complexity required. Okay, too many this term is additional, no, in the calculation, so computations become complex. So that is momentum. Okay, so this momentum, okay, for alpha I think I showed you, sorry, for learning rate I wanted to show you another thing. This I have written the code wherein which what we are trying to see is various regularization attempts that we are trying. What I am trying to do is, I am trying to pass various alpha values. I am creating the alphas in log space. Okay, and these values somewhere here, I pass the values. Where are those? Okay, anyway, you can see it in the graph also. So if your data is like this, for 3 different variations of data, as you can see, if you choose high alpha, notice the decision boundary, it is unable to understand, it is unable to divide the data into 2 categories, 2 classes. If you chose high alpha, see, decision boundary is unable to divide it. Okay, if you decrease the alpha, so that is what we saw here also. No, you can't have higher alpha, you have to have a proper alpha here like this. So if you have higher alpha, the decision boundary keeps on decreasing with decrease in alpha. So here you bring it to certain value. Notice it is able to segregate the data, but here it is still unable to classify. Only when you have proper alpha value, it can do the proper, come up with the proper boundary. Okay, two classes are properly segregated. So this is the impact of alpha. So that's why you have to choose alpha value properly. You can't be very, it can't be very small, it can't be very high. Okay, this is one thing. Second thing is, this I was talking about learning rate initialization. This I will show you in the, when I talk about that just in a bit. Next is momentum. Okay, momentum is what we were talking about, right? Here we have to specify momentum. When you are discussing momentum, you have to specify momentum. What is the momentum value? Different beta values we have provided. Okay, it is 0, 0.0, 0, 0.3, 0, 0.6, 0, 0.9. So notice what is happening here. 0.9 when you specified, momentum is kind of too high here. Okay, I mean from this graph I think it's not properly understandable, but okay. So momentum, if it is 0, training accuracy was lower. Momentum, as you increase the momentum, training accuracy increased, as well as the validation accuracy also increased to certain bit. So this was the better momentum value. 0.6 was the best momentum value. And then after, when you further increased, model started overfitting. What is the overfitting? Overfitting means higher training accuracy, lower testing accuracy or validation accuracy. So your accuracy started decreasing when you increase the momentum. So it is very important that you choose the best momentum. Here the best momentum is 0.6, where in which testing accuracy also increased, training accuracy also increased, and after that it started increasing, this started decreasing. Nothing but model started overfitting. Okay, so this way you can choose the best momentum value. This is the best momentum value. Next, there is a concept of learning initialization. This is what I was trying to show you in the learning rate initialization. Learning rate you chose, whether it is constant or inverse scaling or whatever the value, but you have to also provide a value, no, the learning rate initialized value. So that if you see, default is this value, but it controls the step size. Okay, so that is what I am trying to show you here with different values. What could be the, for example, I am using SGD. Here learning rate I have provided as 0.2. For the same, here I am using the, you can compare the different momentums I have used, momentum and learning rates. So here I have modified the learning initialization to 0.2, but I am using a different momentum. Here momentum is 0. Here I have additionally used Nesterov. I don't know how to pronounce that. Anyway, Nesterov's momentum. Here I have set it as false. Here I have set it as 2. Nothing but I am modifying different momentum parameters to understand how this solver Adam is going to use learning rate initialization. Okay, and I am labeling that constant learning rate, momentum, Nesterov's momentum, inverse scaling. Okay, and finally Adam I am passing. For Adam I am passing it as a black line. Okay, so when I do this, when I run this with various parameters here I have passed, okay, which I have defined above, all these parameters I have passed here, and all I'm doing is I'm just plotting. I'm calculating, I'm fitting that model, and I'm doing the fitting, and I'm appending the results, and I'm plotting. When I do this, notice, so first one is the constant learning. Notice the inverse scaling first, dotted lines. Inverse scaling perform the poorest. Notice the accuracy, on the y-axis there is loss. Loss ideally should decrease, accuracy should increase. For loss function, when you plot loss versus the epochs, which is what we have done here, your curve should be like this. It should decrease with epochs. Here both blue line and black line are doing the best. In least amount of epochs, they are able to decrease the loss. This length of this line should be minimum. In less number of epochs, iterations, they should decrease the loss. That is the aim. Notice inverse scaling. If you choose inverse scaling, it is performing the poorest in all the different scenarios. Okay. For iris dataset, for digits dataset, for moons dataset, for these are all different datasets. Okay. For different datasets, inverse scaling is performing the poorest. Sorry about that. I'm getting hiccups. So inverse scaling learning rate with momentum, with Nesterov's momentum, all of them are not good enough, I would say. Okay, dotted lines. Okay. Next is constant learning rate. Notice constant learning rate will decrease the learning loss function, but it will take lot of time. It is taking 400 epochs, this red line. Here also it is taking a lot of iterations. Okay, here it is decreasing the learning rate, but after that it is not even running. It is failed to decrease the learning loss function. Hence you see the straight line here, and early stopping kicks in and it stops the training process. Here constant learning is not able to decrease the learning rate for circles. Okay, so you can't use constant learning rate either with momentum or basically you can't use constant learning rate, okay, with momentum or without momentum, and inverse scaling is also out of question. Now the next two contenders are Adam and constant learning rate with Nesterov's momentum. Sorry, constant with Nesterov's momentum and Adam. Blue and black line. The competition is between the blue and black line. Notice how the Nesterov momentum has decreased the loss with least number of epochs. So does the Adam. Okay, black line. Here also blue line and black line, they are competing. Okay, they are doing the effective decrease in loss with least amount of epochs values. Here notice Adam is doing far better job than, not far better, but it is doing a better job than blue line, which is Nesterov's momentum. Either Nesterov momentum or Adam. Here also notice, here disadvantage is Nesterov momentum is unable to decrease the loss after certain period of time, because it fails to decrease the loss, it stops, whereas Adam keeps going. Okay, so in all the four different data sets, Adam is the winner. Okay, that's why we prefer using Adam as the solver. Okay, and initialization rate, we set it as in the parameter, as you can see, this learning rate initialization we set it to 0.2. okay, so that is the best value. Did you understand how different solvers are decreasing the loss functions now? Okay, so this way you can choose Adam. Adam is a go-to solver. Anyway, moving on. Let me know if you are getting bored, or if you want me to stop, I will stop. But just give me a hint. Okay. Next is early stopping. Next concept is early stopping. In early stopping, what we do is, as soon as we see that the model starts overfitting, as in it's learning, the training accuracy is increasing, test accuracy, validation accuracy is not increasing. As soon as we detect that, we stop the learning process immediately. That is called as early stopping. Early stopping is a technique to prevent overfitting. As soon as we see that the model no longer learns, going back to these plots, notice the straight path. See, till up until here it decreased the loss in this way. Okay, but here it couldn't decrease further, not much. Okay, that's why the training has been cut off. The training has not been done till 400. It has been cut off till 150 or 175. Okay, that is what we call is a early stopping. The moment you see this, you can immediately say there is early stopping here. Okay, here also there is early stopping for the red line. Notice it is not able to decrease the loss, hence it is stopping the complete training process. Same is for blue line here. It is not able to decrease the loss, it stopped the training here. So this is called as early stopping. This is also early stopping. It is unable to decrease the loss. So the model is thinking, okay, it is further unable to decrease the loss, so I should stop the training. This process is called as early training. Early stopping. Okay, so the model cuts off the training process. It stops right there. Okay, so this prevents overfitting, saves computational resources, improves the model performance. Okay, and how do you incorporate that early stopping? You incorporate that by specifying the early stopping in this here callbacks. When you're defining the fit, when you are calling the fit function, you are providing the x train y train. You are also specifying how much data should be for validation, and you are also specifying how many runs there should be, 50 runs. And you have to specify the callbacks. In the callbacks you have to specify early stopping, and early stopping you have to specify. Okay, here, and you have to monitor what should you monitor: validation loss or accuracy loss, training loss or accuracy of the training, or validation accuracy, anything. Patience is 5. That means 5 iterations you wait and see whether it is validation loss is decreasing or not. That is what patience is. That means it will monitor last 5 values. If they are very closer or very same, it will stop. Okay, and during this entire process, if last 5 values are not changing and the best weights were somewhere above, somewhere in the previous steps, those will be restored. This is how you define the early stopping. First you should define the early stopping, then you should call it in the callbacks. And where is early stopping coming from? It is coming from the callbacks only. TensorFlow model I am using, Keras. This again, don't worry about this I will explain in depth when we talk about deep learning, but for now just understand how we are incorporating early stopping. Each epoch here, it took me at least like although it's showing as 5 ms per step, but it took me a lot of time, even though my PC is quite fast. Okay, still it took a lot of time. So for all these epochs, notice 50 epochs it has run, and it has calculated the training loss versus validation loss. Okay, so immediately you can see it has decreased the training loss, failed to decrease the validation loss. This scenario we call it as overfitting. So this model is not doing a good job, but that's okay. I was trying to show early stopping. Okay, so this model is not doing a good job. Why? Both your blue line and both your red line should be in the same shape, same direction, same shape. Here it is going like this, here it is going like this. So if your validation loss is greater than your training loss, it's overfitting. This is also the same case, overfitting. Here training loss is lower, validation loss is higher, overfitting. Both with or without. So basically the difference is without it is increasing, with early stopping it has stopped. Notice the epochs, it stopped at 10th epoch itself. Here it went all the way through 50 epoch, increasing the validation loss. So this is poorer than this. This I still consider as bad, but this is worse than this bad. Okay, ideally it should have come like this. But anyway, this is just for example. We are not trying to aim for accuracy here. We are just trying to understand the concepts. That's why we are still okay. Okay, so this is how you use early stopping. Clear? Is this clear? So do you want me to stop here, or do you want me to continue? We can stop and come back, or do you want me to continue? You should. We can continue. This is interesting, right? Okay, all right. Next parameter is beta and epsilon. Okay, beta, you remember the momentum we saw, momentum coefficient. This beta is that momentum coefficient. Now the reason why I have included here again is I wanted to show you one slight difference. When you use momentum algorithm, then there is only one beta. We call it as beta momentum coefficient, that takes into account the previous gradients to update the current one. Okay, higher values of beta means we are giving more weightage to the previous gradient. So this will result in the smoother and stable updates. Okay, So this is again the same formula, same exact formula, there is nothing difference. Okay, the same one that we saw above, there is only one beta. But this, when you use atom instead of momentum, if you use atom, now there are two betas, beta 1 and beta 2. Now what they do is, okay, so beta 1 controls the decay rate, learning rate. Sometimes what it does is, it becomes, value becomes so small, it stops learning. Okay, we call it as decay, learning decay. Okay, gradients become very very low or closer to zero. So that is what beta 1 momentum coefficient. Here also we call it as momentum coefficient only, but we call it as beta 1, first momentum coefficient. So that controls that exponential decay. Second one controls the exponential decay for the second moment estimates. So there are apparently two different gradients. Okay, and first one controls for the first one, second one controls for the second one. So the difference is, first one is taking only the, notice there is no squared here, it is only taking the previous gradient into account, whereas the second one, Vt, what we are calling here, which takes into account variance also, variance of the gradients, it takes the squared term. Okay, that is the difference between this one, two gradients. One is considered in the mean squared average. Okay, mean squared average. Okay, variance of the gradients, and beta 2 controls the exponential decay in that. And this is how Adam is using beta 1 and beta 2 to modify the gradients using the learning parameter. Okay, so that is what beta is for. For all others, there is only one beta. For Adam, there are two betas. Next is epsilon. Epsilon is a small constant value that you use in the optimization algorithm. So why do we use this? We use this to avoid zero division error. What happens is, when you are calculating this theta is the weight. You are modifying the weight from the previous one by subtracting the alpha, which is your learning rate, and you are multiplying this as an additional term for Adam. For logistic regression, this all becomes the same except for this term. Except for this term, you have only theta here. Okay, you have theta t minus 1 here. Instead of mt divided by square root of vt plus epsilon, you have only theta term here. For Adam, you have this term instead. Now what we are saying is, if this square root of vt, this term, becomes 0, then this entire term will become 0. There is no learning only then. Okay, zero division error comes. That's why, to avoid the zero division error, we are adding a small epsilon value. It could be 0.001. Okay, whatever the value is. To this enables, if this even if this square root of vt becomes 0, this small epsilon value will ensure that momentum becomes high. And if it becomes high, alpha multiplied by high value becomes high, then gradient becomes high. Okay, this way we can take care of the, we will not let the gradient vanish. Okay, or we will not encounter a zero division error. That's why we are using epsilon. Epsilon is added to the denominator in the update rule to prevent the zero division error that may lead to instability. Okay, typical values are, okay, 10 to the power, okay, I think this is power, okay, 10 to the power of minus 7, nothing but 0.60 then 1. Okay, this is power. I think it hasn't come out properly. Let me write like this instead. 10 to the power of 7 is 10. I will write for now like this. Okay, we will 10 power 8. Okay, we'll write like this for now. So what are the advantages? Beta is used to smoothen the updates process and increase the convergence, reduce the oscillations. Disadvantages is you have to tune it properly. Epsilon is it avoids the zero division error, adds the stability to the calculation, it improves the robustness of optimization algorithm. Okay, disadvantage is it plays minimal part in the performance. Okay, either you choose very large or small may affect the numerical precision. Okay, so that is the thing. Next is the vanishing gradient problem. Okay, see, you have to understand what we are doing is we are just playing around with the weights in this entire neural network process. Even in logistic regression, we are playing around with slopes. We are just modifying slopes and trying to decrease the loss. That is what is happening. First understand what a gradient is. Gradient is this one only. This is theta is here, it is weight. You are modifying the weight by doing some minor decreasing here. Okay, that this after you decrease that weight becomes a gradient. Okay, now what we are saying is vanishing gradient problem. Vanishing gradient problem means especially when you have too many layers, too many hidden layers, and mostly seen in RNNs and deep forward feed forward neural networks. As the number of hidden layers increase, if you are decreasing this multiple times, let's just say 1,000 times you are decreasing, what will happen to this theta? First of all, theta is between 0 and 1. Okay, 0.55, let's just say. If you decrease that value by minor values by 1,000 times, what will happen to theta? It will become 0, no? It will come very closer to 0. First of all, it is 0.5. And then you are subtracting too many times from that 0.5. It will become 0.00 something, some value, some 1 or 2 or whatever. That problem we are calling as vanishing gradient problem. When your weights itself become 0, then the model no longer learns. Okay, so this process is done during back propagation. Okay, so what we are saying is vanishing gradient problem is nothing but when you have too many layers, hidden layers in certain type of networks, your gradients appear to become very small, exceedingly small. Okay, thus preventing the network from learning. Every time you hear the word learning, you understand you're finding the weights, optimizing the weights. Okay, and that process, if weights itself become 0, what learning will remain? There is no learning there, and your entire back propagation is useless if your weights become 0. That process, situation is called as vanishing gradient, and we already learnt about how to solve that problem. How to solve that problem? Vanishing gradient we saw above by using leaky ReLU, right? Activation function you have to modify. If you use a activation function as leaky ReLU, okay, not leaky ReLU, it solves dying leaky problem. Vanishing gradient is you have to use ReLU. Okay, ReLU reduces the likelihood of vanishing gradient. What ReLU is doing is, ReLU is saying if my input is above 0, which is positive, if my input is 0.5, I will give the output as 0.5 only. This way, okay, the same value, you don't have to differentiate now. You don't have to modify that 0.5 by subtracting some small value 1,000 times to make it much smaller. Instead, what we are saying is if that value is positive, I will return it as positive only. I will not touch that. I will not modify it. But if that value is less than 0, negative value, then I will keep it as 0. No need to differentiate again. I will simply mark it as 0. Okay, that is what leaky ReLU is doing. That is how you take care of this vanishing gradient problem. Okay, understood? Did you? So you can read it here. So when you are training and back propagating the errors, that is loss, okay, what happens is gradients are calculated at each layer, and those gradients are multiplied by weights. Gradient is alpha into some weight value, that is multiplied by weights, and you are updating that weights by subtracting that. So nothing but this equation only. You are taking the alpha, multiplying to the theta. So usually it will be theta. Here in this case you have different term. Anyway, so you are multiplying with to that variation of the theta, and you are subtracting from the theta only. from the theta of previous step, and that will give you the theta of current step. So when you're doing that, okay, what happens is these values become very small, nothing but what I just said now, repeated. So because you're doing it multiplication, subtraction and multiplication multiple times, those values will become decrease very very much, okay, and they'll diminish. Hence we are saying they'll diminish exponentially. So if they become exponentially small, there is no learning, okay. You can't further differentiate the further smaller values. And how do we avoid this problem? We use ReLU. Okay, very simple. ReLU or even leaky ReLU. Okay, so they don't decrease the values. If your value is positive like 0 0.5, 0 0.6, 0 0.1, 0 0.2, the output will be given as 0.2 only. No decreasing. Okay. There are other activation functions as well called swish and mish. Okay, those also will help in solving the effective gradient descent problem effectively. Another thing you can do is you can do weight initialization. This is what I was talking about. H initialization, also called as chiming initialization. It is suitable for ReLU activation. If you see sigmoid or tan H, if you are using, then you have to do Xavier initialization or Glorot initialization. By doing these initializations, you will be effectively solving that vanishing gradient problem, and it's a serious problem. You have to solve it. Otherwise, what will happen? You'll get like this. The model won't generalize. The model won't work properly. Next is batch normalization. Also, you can do 2 times I have. For batch normalization, also you can be done. Here, what is happening is you are normalizing the input layer. That also will help you in. We'll see what normalization is, but that will also help you solve in vanishing gradient problem. Next is ResNets, residual networks. In residual networks, we have something called skip connections. Okay, if you are working on ResNets, residual networks, it's a different type of neural network. You have to use skip connections. Skip connections will allow the gradient to flow directly throughout the network without modification. Okay, it will bypass some layers. Okay, thereby it will nothing but between first hidden layer and the 7th hidden layer, you will not modify it, you will copy paste as is. That's what skip connection means. Okay, next is gradient clipping. Clipping also can be done. Clipping means if your gradients become too small, then you are adding a capping value. Okay, beyond this value, if it decreases, you will retain that capped value. Let's just say your gradient value is 0.8, and your capping value is 0.2. You will differentiate it up until that 0.8 becomes 0.2. If it decreases beyond 0.2, you will retain the gradient as 0.2 only. That is called as clipping. Okay, capping, clipping, whatever you call it. So that is what it is. Now, how do you do the initialization? This initialization I talked about, H initialization, Glorot initialization, is done like this. Where is that? Okay, we'll go step by step. So one way of solving it is, see, this is your simple neural network. You have linear layer, and then sigmoid for binary classification. Okay, finally for forwarding you have sigmoid. Okay, at each layer. How do you first see this one? This code is without any solution for vanishing gradient descent. I have not incorporated any of these. Hence, we see the vanishing gradient problem. See the gradients. First of all, they are very small, and for if you increase the epochs, they are further decreasing. Right? That is what you see. You are seeing the decrease in the epochs. They are approaching closer to 0, and now there is no learning in the model. No matter how many epochs you run, there is no learning. This is vanishing gradient problem. Now, for first solution to that is changing the activation function to ReLU, leaky ReLU, PReLU, LU. So I have changed. Okay, I've added this additional activation function. And when you run the epochs once again, Notice the difference between 33 and 28. It is not big. Here you notice 11 to 5, it is decreasing, although it is here also there is not much difference. They were already small, but as you can see, these activation functions like ReLU, they are not completely decreasing, but they are kind of modifying slightly. Slow modification is there here. Okay, I mean they these I should have started at much higher value, but anyway, but what I'm trying to show is ReLU will control this problem to certain extent by slowing down the vanishing gradient problem. Okay, although you can't yeah, so here maybe you can see leaky ReLU from 35 to 30 it has gone. Ideally without leaky ReLU it would have gone from 35 to 5. 0.005 0.0005 it would have become from 0.0035, but this is to certain extent it is controlling the decrease in the vanishing gradient. Okay, here ReLU is doing better job. Okay, ReLU is doing better job. It came to this point. Okay, it started increasing the gradient values, okay, by retaining the gradients. So this is how it should be. Okay, next is gradients with LU is not doing good job. It is okay, again from 50 to 40 to 42 only it has gone. It has not gone from 50 to 0.0005. Okay, sudden decrease is not there. Okay, this way activation functions control, okay, control the vanishing gradient problem. Is it understood? Clear? Any questions up until this point? I want to stop it here.